if you have any questions, there will be a link in the chat where you can ask questions on our Swift forums afterwards. So please do that. Okay, so with that, let's dive in with distributed systems in Swift. So quick intro, just in case you haven't seen Swift all that much. I know it's not as popular on the server as it perhaps should be. So it's a native language. It kind of originated from, on the devices that Apple develops, but it's very much a multi-platform language. So you can use it on Linux. It's fully supported there, and we're still working on Windows. This is like almost there. And the cool thing about Swift is that you get this high performance, low-level runtime, native code, direct calling into C, all that good stuff. But also the language is a very, very high level, what you would expect from a modern functional language. So you get kind of Scala-like power in the language, but with very, very little overheads. We have some cool things like copy on write data structures, so you get the benefits of what you would normally have to do, copy data all the time, but we do it much more efficiently. We have value types in the language, and since recently, actors and concurrency, which is a part of the talk today. So as we dive in, I always think about distributed systems as being two things, really. They're hard and they're everywhere. And that's a big problem if you combine the two, because more and more people have to write distributed systems, but it's really hard to get into and keep them, running and, scalable and understandable, which is a big thing I care about personally. So there's a few things we identified that are kind of problems we can address. And the primary one is, in Swift, we care about something we call progressive disclosure. So it means that as you learn the language, as you, build your project, there's maybe more and more things you have to take care of, but it kind of comes in phases. You don't have to immediately know about distributed systems if you're just writing a Hello World app, right? And this learning curve should be kind of linear. There shouldn't be like a huge gap between, going from concurrency to distribution, and suddenly you have to throw out everything you ever built and rebuild everything. So we want to address that a little bit. Another issue is that obviously going distributed, there's way more failure scenarios to think about. Obviously, there's networking involved, so there could be both network delays, message drops, all kinds of issues. And as you're kind of coming from, not thinking distributed all the time, it can be difficult to cross that chasm. And maybe you'll forget one or two failure scenarios, and suddenly you're, woken up with issues in production. Not fun. Obviously, people know about that, so they solve these things, but very often it ends up as a lot of boilerplate, a lot of serialization networking code, kind of swallowing up and entangling your business logic. Of course, you can say, well, you should have separated out the layers, and many teams do, but that again ends up with very much like sometimes ad hoc solutions. We've all seen that, like a small startup suddenly has to grow. They only know MySQL, they suddenly use, MySQL as a queue, or, random ad hoc solutions which work good enough, but they're not really the end game. And then you have to do a big rewrite, right? So this is, again, there's no linear progression. And they're hard to reason about, test, and debug, because the tools you use to build them are so different from what you're using in local programming. So we want to simplify all of that. We want to simplify distributed systems programming and push the state of the art a little bit as we do that. So we kind of did that, pushing the state of the art with our actor runtime recently, which we introduced in Swift 5.5. That's the current stable release. And as part of Swift concurrency efforts, we introduced actors to the language. So actors you probably have seen or heard about at least a little bit. There's the known implementations like obviously Erlang, the OTP, Orleans or Akka. The big difference from a lot of other implementations that you may have seen around is that actors are part of the language in Swift. So you really can declare actor greeter the same way you would declare a struct, a class, an enum, and that has specific implications on the type system and runtime. So this is how you declare an actor. An actor's purpose in life is to isolate state, and how it does that is through asynchronous messaging. this messaging we express as functions on these actors, and they basically become asynchronous tasks that the actor can execute. So Swift catches isolation issues. So we always talk about actor isolation when we speak about that. And here's a simple isolation violation that basically you get a greeter passed around, you try to access this variable, but an actor's purpose in life is to prevent you from racy access to such a shared variable. So the compiler will catch that and say, well, you're trying to access this actor isolated property. You can't do that. This would have been racy. This is a very simple example. And you could have done that with just putting private there. But this isolation checking is much more contextual than just access control. Let's dive right in to cross-actor calls, where this becomes slightly more apparent. So actors isolate their state, and you have a function greet on this greeter, and it returns a string. Now, if you call this greet on another actor, so here we created a new actor, we call greet on it, that is a asynchronous call, because that's how actors work. They do asynchronous communication. So if you want to call greet, you have to call that. Actor eventually processes this request, processes that, returns you the string. And we do that by implicitly noticing, oh, that's an actor call, so you'll have to await on it. And that's the classical async await model you may be familiar with from other languages. We recently introduced that to Swift. And it kind of plays very well with actors, actually. Now, the other side of it is we can also do, so here's an extension. So you can add functions to actors like that. And we can do one of two things. The first example is an asynchronous function. You can see the async word there. And we call this greet function on self, basically. Because we are already inside the actor, that function is not asynchronous, right? You just call it directly. If, however, you wanted to call an asynchronous function, so something that was declared explicitly asynchronous, then of course you would have to await on it, right? Classic async await. But we have this notion of inside and outside actors a little bit. And it kind of implicitly adds effects to invocations. So, so far so good. You could have maybe done this in different ways. But here's where the language integration really shines. So we're also aware of kind of closures and where they execute. So here we have this greet function, and I want to increment this greeted counter, but I want to do it later. At some point, I would just want to return the hello name as soon as possible and then increment this counter. Silly example, but this is racy, right? Because this dispatch queue global, that's going to run on a different thread. This would have been racy. So the compiler can know that and can prevent you from doing such an racy access. And we call this sendability checking. So basically we're checking, well, this closure is sendable, it could be executing somewhere else, so this isn't safe. Of course, you have ways to express what I just said, that oh, I want to run this thing later on this actor, and that interrupts very well with the rest of Swift's concurrency, where we have tasks. So task, if it's kicked off from an actor, it will execute on this actor. So this way you can get the safety back. That's all I will cover about Swift concurrency today, but because that's all we need for the distribution part. But if you want to read more, there's really a ton of really cool stuff to learn, especially structured concurrency. I think is very cool because we're probably the first language to take it all the way into the language with static checks and like that. So it's very exciting. But the next step is, of course, distribution. So we have an experimental language feature that's available today in nightly toolchains called distributed actors, which, of course, when you think actors, you often think distribution. And I'll introduce a little bit how to use them, how we represent them at runtime, and then we'll dive into some examples. So the idea is that we want to have this nice learning curve where, okay, I know how to program with actors, I know about state isolation, I know that these greet invocations basically get turned into something that actor then later executes. And distribution is very similar to that, right? So in order to make your code distributed ready, you just need to make the actor distributed. So now it's a distributed actor. and distributed actors can declare distributed functions. We'll talk a little bit about why that needs to be explicit, but I actually think it's very, very important and good that we have this explicit and not just magically turn things into remote calls. That's not what we want. We want to be very explicit about what is remote and what not, right? So here we have basically a ready-to-go distributed actor. And let's talk about what that gave you. So the first thing that gave you, a distributed actor gains the property of location transparency. So location transparency is this way to think about your program and objects where you don't care where they're located. So it could be located on the same host you're executing or on a remote host. And even more so, maybe it's not actively running yet, but you can treat it as such, and maybe the other side can kind of spawn it on demand. That's a very interesting pattern. We don't have implemented yet, but you can totally do that, right? So you program against, at least statically, against the distributed actor model, but at runtime, of course, there's two actual real cases. So the actor is either actually local, in which case it's the exact same execution semantics as the normal actor in the language, or it's a remote actor, in which case invocations of distributed functions don't actually invoke the code, but they become messages that we put on the wire, and the remote instance actually gets and executes that. We'll talk about how we do that in a second. So distributed actors not only have to turn things into messages, they have to enforce slightly stricter isolation. So similar to the previous example, a distributed actor is an actor. So like the var greeted is isolated the same way you would expect, but there's two additional rules to isolation. In our, I will call it quote unquote local only actors, the access to the let local ID 13 would be allowed because we have the guarantee that this is a constant property of a sendable type. This will never change. So we don't even care to hop to the actor for execution if we wanted to reach that local ID. That's very useful if you think about it, because you very often want to print, okay, what actor is that, right? Some user ID. What actor am I interacting with? So you need something. You wouldn't want to hop to the actor only to print it out in a debug statement. Doesn't make sense. So we have this. But in distribution, you cannot ever access such state. So we prevent that. And you cannot access any non-distributed functions, of course, because we don't guarantee that they can actually be distributed. You can pass closures to functions after all, and distributed functions would reject passing things that we know we cannot serialize. So that's the two additional rules in type checking. There's more to that. I'll have a few more examples. And yeah, the greet, of course, you can call because it's a distributed func. There's a little bit more to a distributed actor. So we add two implicit properties, which are non-isolated vars. That means you can access them, again, without hopping to the actor. And one of them is the identity. As I kind of said with the user pattern, where you want to print out, hey, what actor am I interacting with? Distributed actors always have an identity. The specific identity depends on the transport you're using. Maybe it's just an integer if you're an IPC system. Maybe it's a URI if you're kind of distributed, but you want to point at a specific one. Or maybe it's just a name if you just want to express the concept of a specific named remote greeter. So we inject those two properties for you, and we enforce that they're always initialized. Now, the other thing that distributed functions do is, as I hinted at, they guarantee that we can actually form a message for the message this is kind of describing. So here the greet takes a full name, and that full name is a struct, as you can see here, but it's not codable. So codable is a protocol in Swift. Protocols are similar to interfaces. Just very briefly, and more or less, they're a bit more powerful than that. But very briefly, they're like interfaces. So it doesn't conform to codable. And codable is our way of expressing, at compile time, we know we can structurally prove we can serialize this. And it's detached from any specific encoding scheme. So at runtime, you can say, hey, encode this using a binary, whatever encoder, or JSON if you want. But we need to prove to the compiler that we can do that. So we very easily just add codable, the compiler is happy, and we're kind of guaranteed that we can form messages for these things. Certain things, like, closures, you can't make that codable, etc., etc. And the compiler helps you out with doing the right thing here. Now, the other effect of distributed functions is on the call sites. If you just have a local actor greeter, you declare this greet func. We saw already that this causes async await across actor boundaries, right? So you have to await this greet call. What distributed calls cause is not only is it asynchronous, because there's going to be networking involved, it's also throwing. So Swift's error handling is fairly interesting. So errors in Swift are values, so they're very cheap to construct and carry around, same as returning a value. They're not as heavy, they don't have like full stack traces. And we kind of mark call sites that may be throwing, so you're informed that this call, okay, this could be throwing. It's not as rigid as you may be worried now. Oh my God, is this like checked exceptions in Java? It's not as rigid. So you just have to acknowledge that you're either handling or escalating. You don't have to be fully typed about this. And I think that's a very good trade-off we're making here. Okay. We have things in the type system where you can express, well, I actually know this remote actor is definitely local, and the type system is then aware of that and wouldn't cause this implicit effect of throwing, because that only comes from the networking side of things. If you declare that function to be throwing, it's of course always throwing because it's your errors. Now, runtime. So the interesting bit comparing a language integrated actual runtime with just a library one is how kind of native it feels. It's just normal functions, just normal calls, and how efficient it is in the representation. So here I show how you can get a resolve a remote reference. So you get an identity that somehow uniquely identifies some worker actor in the cluster. You pass some cluster transport, and you either get a local reference or a remote reference. The important bit is you never always get a remote reference back. We kind of uphold this location transparency idea here, because you want to write this code once and then run it maybe locally in testing in a single node. But when you deploy, well, these actors would be actually remote, right? So you code against distribution, but runtime is remote or local, right? Now, here's the cool thing we can do. Because this is so well integrated with the runtime and literally how we allocate objects, remote instances obviously take minimal storage space. We do allocate storage for the transport and identifier, as I showed before, but we don't allocate any storage for the actors, whatever state it wants to have, right? Obviously. The important bit here is that this is very much ingrained with the rest of the Swift runtime, and tools like debuggers or anything else can be aware of that. You're trying to, in LLDB, print an actor. Well, we're not going to give you state because it doesn't have state, right? So we can really go deep and wide with these integrations. Now, remote calls. Calls work like that. You literally call the function. If it's local, we just invoke it. If it's remote, we call this func that kind of creates a message representation and calls a specific transport this actor was created with to send a message using it. The details are in the middle of evolution, so that's still changing, but that's the idea. Now, this is the language feature, but just a language feature, can't really do anything. So we still need a cluster runtime. For example, a cluster runtime. You could imagine other ones because the language feature is kind of agnostic to what transport you're using. But the most typical application of distributed actors is really these clustered environments. So I'm more than happy to announce that today we're open sourcing a complete clustering library. It's available probably right now or in like 10 minutes or so. Should be there after my talk on GitHub Apple, Swift distributed actors. You can give it a look. And what is that? So it's an implementation of this actor transport protocol that I mentioned before, with the idea of, okay, you can program as if your cluster is just like a very, very big machine, right? That's the general idea of distributed actors. And we implement all of the core building blocks you would expect from such a runtime. Conceptually, again, I mentioned all the other runtimes, conceptually similar to those listed here and implemented using Swift Neo, which is kind of the Netty of Swift, actually kicked off by Norman, the original author, well, the main maintainer of Netty, has kicked off the Swift Neo effort. And now it has a full and proper amazing team taking care of that. So we have a really great high performance runtime to base this all on. So I want to highlight 2 or 3 features today, what this actually gives you. How do you locate your distributed actors? How do you react to their failure? And how you can interact with the cluster itself a little bit. Because finding actors is the first thing people ask when they saw the language proposal, which we put out there earlier, but we didn't announce that we have a full implementation yet. Well, today we can share how you can solve these difficult problems that we solve for you. So discovering actors basically means that you have to find these identities so you can call resolve on them and get these actors back, right? But we provide a higher level abstraction. We call it the receptionist pattern because, like a reception in a hotel, actors have to register at it and then check in and check out, basically. So as you start your actor and you're in it, you can say receptionist register self with some key. And on another actor system, a node, you can basically do system receptionist, subscribe to workers. And this gives you an asynchronous stream that will keep giving you actors as they join the cluster. And then you can invoke receive worker. How it works in practice is this. New node joins, the receptionists are gossiping around about those actors. We have 2 actors on different nodes there. We eventually get to know about them, and we invoke these receive worker in the async stream you see running there. Fairly typical. Just really well integrated in the language. I think that's really cool, actually. So the other thing is, obviously, if you find actors, a big piece of distribution is that everything fails all the time. So how do you react to that? Again, we provide this as an abstraction where you only have to think about actors, right? So you have your worker and you want to watch the greeter, and whenever a greeter terminates, you want to basically remove it from this set, right? Simple logic. You can imagine a worker pool or something like that. And the interesting bit here is that either the deinitialization of a remote actor or a local actor, for that matter, triggers first termination. So, just actors coming up and going down naturally triggers this termination signal, so you can remove them from the worker pool. Or if an entire node dies, the entire node D is hosted a bunch of actors, terminates, then we have failure detectors that trigger and we notify you about specific actors having failed. We do that by assuming, well, the entire node is down, so all of the actors that were known to be living on those nodes are terminated, and we inform all the other actors that have been watching them. So you never really have to think about specific cluster events per se. You just program against actors. So that's really nice. We kind of collapsed the failure space into, you just have to care about actors, not about specific things happening in the cluster. You can care if you want to. And the lower level of that is implemented using Swift Cluster Membership. That's a library we open sourced earlier last year. And it implements the swim failure detection with lifeguard extensions inspired by our people at HashiCorp. They did a really good job with that. And how that failure detector works is a bit smarter than just your plain old failure detection. So it pings directly a potentially failed node using like a heart beating mechanism. But if you fail contacting that, we ask other nodes if they also think that node is unhealthy. Because very often in such systems, it can be that so node A, is actually unhealthy and was just not processing the EC responses in time. So we this way can reduce the force failure detection by quite a much. So we do that, and eventually we mark a node down. When it becomes down, we issue this terminated signal about the actor. If you want to dive in really deep, the actor members have a specific life cycle. What I just talked about is reachability, and you can plug in your own failure detector And the purpose of the failure detector is to move nodes between reachable and unreachable. And then we have another pluggable mechanism that's a downing strategy. And the downing strategy's purpose is to observe these events and eventually issue a down command. And again, once you issue down, we automatically handle all the termination messages for you. So you can go low level, exchange any of those pieces if you want. And this is kind of prepared. You can go and deploy this on bare metal. You don't necessarily need a full, Kubernetes, whatever, to manage health for you. We have that. If you want to, you can just plug it in here. So it's very extensible. And how do you consume these events? You've already seen an async stream, but you basically get an async stream of cluster events. You can subscribe to that and apply changes to the membership. Every time you apply a change to the membership, you get a change event that tells you, well, what was the change? And you can know, oh, leadership changed, oh, reachability changed, things like that. And lastly, a real world example, building a worker pool with all of these things. You have a worker, it does some work on some work item, and then you want to have a worker pool. So it just has a set of workers. And what it does is, firstly, it subscribes to all the workers in the cluster, adds them to the set. It watches them for termination. So when they die or their nodes die, you remove them from the set. And your kind of balancing work across the cluster is as simple as just picking a random worker and forwarding the work to it. That's all you need to do, really. Obviously, you can get much more fancy than that, but this is the basic, really, to get something running. And the cool thing is, because all of the networking and all of the serialization is kind of encapsulated in the transports, we only have to instrument it once for distributed tracing. And tomorrow, there is a talk by Tim. Tim is a part of a server-side Swift work group about distributed tracing. And if you want to see that in action, he also has a production system using these things. I highly recommend checking that out. And again, I think it's very important to highlight that tracing is great, we know that, but it's always so hard to integrate in an ecosystem, right? That's usually what prevents people from using tracing at all. So what we have in Swift is, again, language features that are specifically tailored to make tracing in instrumentation systems easy and robust. So that's task local values, another feature we introduced this year in Swift. Highly recommended you check out that talk. Especially task local values are kind of novel. That's not something you have in other concurrency runtimes, and they prevent tons of bugs you normally have with thread locals, right? They're much better than that. Okay, with that, I want to quickly sum up. That's the slide we had before with all of the issues. So we said going distributed is too hard to learn. So with distributed actors, you don't necessarily reuse the code, and it's still very different because you have to think about distribution, but you reuse some of the skills. It's still the actor model, you still use the same semantic way of reasoning about things. So it's much easier to adopt distributed systems for people. There's less failure scenarios, there's less specific failure scenarios you have to think about, because there's, again, just normal functions throwing and actor termination if you want to care about it. There's no error-prone entangling of business logic and networking code because we encapsulate it all in the transport, which again you can configure, but it's far away from your business logic. There's no more ad hoc solutions by teams because we can collaborate and write reusable Swift code and reusable Swift algorithms against distributed actor protocols, and we can use that in various scenarios, even across different transports if you want to. And it's easier to reason about because you can test it locally. Distributed actors are super easy to test just in unit tests. You can have unit tests for a distributed system, inject failures, anything you want. And tracing is trivial to build in, so you have a very good production experience as well. So this is available today. It is an experimental language feature, so you do need to use nightly tool chains, and a little bit of the build process is slightly annoying right now. That's because we're kind of bringing up the language features still as we evolve the library. But please have a look. I'm more than interested in hearing all your feedback. All the questions and ideas you might have, please use the Swift forums. I'll be more than happy to catch up with you over there. That's all I got. That's the links to follow to the forums and repository. And thank you very much for your time.